gradient problem makes it hard for the network to remember information from earlier in the sequence. So as I said, for the solution we can use LSTM, which is a long short-term memory. LSTM networks introduce a more complex architecture with gates and a memory cell that allows information to flow more effectively over long sequences. This helps mitigate the vanishing gradient problem. Or we can also use gated recurrent unit. This is a simplified version of LSTM. GRUs also use gating mechanisms to control the flow of information, making them effective for handling long-term dependencies. Or we can go for gradient clipping. Like this is where during training, clip gradients to a maximum threshold to prevent them from becoming too small or too large. This is pretty much about vanishing gradient problem. Moving on, we have exploding gradient problem. In this, so what is the exploding gradient problem? This happens when gradients grow too large during back propagation, leading to unstable training. It can cause the model's weights to become excessively large, resulting in poor performance and model instability. Its impact on training includes, in severe cases, exploding gradients can make the training process fail entirely, leading to erratic or unpredictable behavior in the model. And the solutions for this is gradient clipping or proper initialization. But before going to the gradient problem solutions, I'd like to say more about it. So exploding gradient problem occurs during the training of deep neural networks, particularly in RNNs when gradients become excessively large, like I've said already. This can lead to unstable training, causing the model's weights to update inappropriately, making the loss function diverge instead of converge. In back propagation through time for RNNs, gradients of the loss function are calculated for each time step. These gradients are propagated backward through the network by applying the chain rule. If the gradients at each step are consistently greater than 1, their repeated multiplication can cause the gradients to grow up exponentially, resulting in extremely large values. Mathematically, for an RNN, the grade value is of loss L with respect to W time step can be expressed through a formula again. And now coming to the consequences of exploding gradients. First one is unstable training. The network weights can change dramatically during training, making it hard for the model to converge. Second is loss divergence. The loss function can increase to very large values, preventing the model from learning meaningful patterns. Next, we have numerical instability. Very large gradients can cause numerical overflow, leading to not a number values in computations. Here is an example for exploding gradients. Suppose we are training an RNN for a sequence prediction task. If a particular weight's gradient becomes extremely large, it may cause the model to update the weight drastically, making subsequent predictions widely inaccurate. This can prevent the model from learning or cause it diverge. So now comes to the solutions. We can use gradient clipping. The most common solution is to clip gradients to a predefined threshold. This prevents them from exceeding a certain magnitude. Weight regularization. Adding L to regularization, weight decay, which means can help control the size of weights and gradients. Third up, we have proper weight initialization. Using appropriate initialization techniques like Xavier or Glorot initialization can reduce the likelihood of large gradients. Reducing learning rate. A smaller learning rate can help prevent large updates caused by exploding gradients. And normalization techniques. Applying batch normalization or layer normalization can stabilize the gradient flow by normalizing the activations at each layer. So to give a summary of exploding gradient problem, this occurs when gradients grow excessively large, like I've said already. It leads to unstable training and divergence. This can be mitigated through techniques like gradient clipping, weight regularization, and proper initialization. By managing gradient magnitudes, training becomes more stable and effective, especially for deep and recurrent neural networks. Moving on, we have RNN LSTM with time series data. So here I've used time series data, which represents values recorded over time, like example stock prices. Why LSTM? So along short-term memory networks are ideal for time series prediction because they can remember long-term patterns. Here the objective is to forecast my TCS stock prices using an LSTM model trained on historical data. I have taken a TCS stock price data for this. So coming to the dataset overview, TCS stock price dataset. TCS stock price is from August 11th, 2002 to September 29th, 2021. This features the daily closing prices, and the purpose is to use past stock prices to predict future trends and compare the predicted results with actual data. Coming to the model architecture overview, this has an input layer of 30 time steps and one feature, LSTM layers of about 4 layers with each with 50 nodes, and then we have dropout layers, 3 layers each with 0.1 dropout rate to reduce overfitting, and lastly the output layer, a single data dense layer predicting one future value. Now here the training batch size is about 15 and epochs are about 10. Input layer configuration, single feature, that is the closing price. Input shape is about sequences of 30 consecutive days used to predict the next day's stock price. Importance is the length of the input sequence helps the model capture patterns over the recent past. Next, we have the LSTM layers explained. So in LSTM 1, it has about 50 nodes, return sequences for the next layer. In LSTM 2, we have again 15 nodes, continuous processing sequences. In LSTM 3, I again got 50 nodes, learns complex temporal patterns. And in the final LSTM layer, which is the LSTM 4, outputs the processed sequence for prediction. Moving on, here are the dropout layers for overfitting control. The dropout rate is 0.1 applied after each LSTM layer. Function is randomly drops nodes during training to avoid overfitting. And the impact would be it helps generalize the model to new data. Output layer and model prediction. Dense layer. Coming to the dense layer, one node to predict a single future stock price. Output is the forecast of the next day's closing price. Minimize prediction errors using error metrics like RMSE and MAE. Then the data is configured for training. Here the input sequence is 30 time steps for training and testing. Batch sizes would be 15 samples per batch for training and 1 sample per batch for testing, and 10 iterations through the data set, that is the epochs. Coming to the model training process, first one would be preparation. So scale and reshape data to fit the LSTM model. We feed 30-day sequences to predict the next day's price. We run for the 10 epochs to allow the model to learn patterns, and the model adjusts weights to reduce the prediction errors. Coming to the model diagram, visual representation is first we give the input, then we have the LSTM layers, then we have the dropout layers, and lastly we get the output. It shows the sequential flow of data through the LSTM network. It highlights how the data is processed and transformed through each layer. Coming to the model evaluation metrics, first one we have the root mean squared error. It measures the prediction error magnitude. Then we have mean absolute error, which measures the average absolute errors. Then we have the importance, which is the low RMSE and MAE indicate better predictions. Next we have the forecast results, which is a 100-day prediction. Graph, it gives us the predicted versus actual TCS stock prices for 100 days. Observation is the model captures general trends but struggles with sudden changes. Here the reason would be the stock prices are influenced by unpredictable factors like news or market sentiment. Next we have model limitations. Struggles with the sudden price jumps and drops. External factors are market sentiment, news, and economic conditions affect stock prices. And the challenge would be LSTM models rely solely on historical data, missing real-world influences. To improve the forecast model, we add features which is incorporates news sentiment, technical indicators or volume data, hyperparameter tuning, which is adjusting the learning rate, epochs or dropout rate. Alternative models is again trying the gated recurrent units or hybrid models for better accuracy. So coming to the conclusion and future scope, summary of the key points would be the dataset and model demonstrated how to handle time series prediction using an RNN, focusing on both practical implementation and addressing common training issues like vanishing and exploding gradients. Using a sine wave dataset helped introduce the concepts before applying them to the US Housing Price Index. Future work would be further exploration can be done by applying more complex models like long short-term memory or gated recurrent units, which are designed to handle long-range dependencies in time series data more effectively. This approach can also be extended to forecast other financial or economic time series data such as stock prices or market indices. And the summary for LSTMs would be LSTM effectively captures overall trends in the TCS stock prices. The next steps would be to integrate more data sources for improved accuracy, experiment with model architecture to reduce errors, and the goal is to build a more robust model for reliable stock price forecasting. And the overall conclusion for recurrent neural networks would be RNNs are powerful neural network architectures designed for handling sequential data such as time series, language, and audio processing. Their ability to maintain a hidden state that captures context and relationships between sequential elements makes them suitable for tasks involving time-dependent or context-dependent data. The strengths of RNN would be sequence handling. RNN excel at tasks where data comes in sequences such as text, speech, and time series forecasting. Parameter sharing. The same weights are used across different timestamps, making RNNs efficient for learning patterns in sequential data. Context awareness. They can remember previous inputs through their hidden state, making them effective for tasks where context matters. The challenges would be the ones that we've discussed: the vanishing and exploding gradients, difficulty with long sequences. So basic RNNs struggle to capture long-term dependencies due to the gradient issues. Training complexity. Training RNNs can be computationally intensive, especially for long sequences. The solutions would be the LSTM GRU that we've discussed, and others would be bidirectional RNNs, which are the process sequences both forward and backward, improving the performance in tasks like language and modeling. Attention mechanisms allow the network to focus on different parts of the input sequence dynamically, enhancing performance on complex tasks like machine translation. So where we can apply RNNs would be the natural language processing, which involves language modeling, sentiment analysis, and machine translation, speech recognition, time series forecasting, music generation, video analysis, etc. This is pretty much about the project that I have done. I've covered almost all the topics that I've used and how well I've used RNNs in my project. I'd like to thank Professor Tuan for giving me an opportunity to take this class in this semester, and all my co-peers who had helped me work on assignments and everything. Thank you so much. Thank you all.